Okay, I'd say we can start now. Nice. Okay. First of all, hello everyone. I'm happy to have you here tonight for this very, very important event. Um, I'm Mario. I'm the DSC lead, or actually the GDSC lead for this year at Politecnico di Milano. And this is an event series that was very requested. It is the ML intermediate track. So what you're going to be learning, which I know basically nothing about, so don't take my word on that, is the basics of AI and ML, and then work on those basics to get to a more advanced level. And this series of events, unlike the one from last year, which was the beginner's track, contains two workshops which will be hands-on. So next Tuesday and next Thursday will be the next two events of the series where you'll actually get your hands dirty with some code. Um, as we said in our emails and on the event page, you will have to have watched our beginner's track from last year, or actually it is very suggested because we are going to be skipping on some of the very basics of these concepts for this intermediate track, and you have to know more or less Python. So if you don't know what Python is, just go and study it a bit. There are plenty of resources online to do that, and if you know Python instead, then you're good to go. The only other requirement, and that's an actual requirement, is to have a Google account, because we will be using Google Colab to program collaboratively. So you'll have to have a Google account for that. One just quick mention before we start. We are seeing that not a lot of people seem to be receiving our emails, or they do but don't open them. So if there's anything wrong with that, just let us know on our Telegram group and ask us any questions or concerns, and we will try to solve them as well as we can. So now, without further ado, I'd like to introduce you Jacopo and Virginia, which were the hosts for last year's. Actually, Jacopo was the host for last year's beginner's track, and Virginia is a new face here. So I'll let them introduce themselves and what they do, which they surely know better than I do. And we'll see you at the end of the event for a follow up. Okay?
Thanks, Mario. So it's awesome to be here. I hope you all can hear me well. Please type something in the chat so that we can solve any technical problems. Anyway, today I'm here with Virginia, so that's great to be here with her and to actually host the second of a series of seminars on machine learning. So we now have the second seminar, which is super interesting. As Mari said, we'll get our hands dirty, especially in the next two sessions. But let me introduce myself. I see Virginia's video was stopped, so while she reconnects, it also says my internet connection is stable. Can you actually hear me? Can you type something in the chat if you can hear me? Yes, fantastic. So I'll just move on. Fantastic. Thanks a lot for the collaboration. So let me introduce myself while we also wait for Virginia to get back with us. I'm Jacopo, and you probably know me because you've attended last year's seminar, or you've watched the beginners track already on YouTube. So if you have attended that or you watched that, I really hope you enjoyed it. This one will be way more interesting, I hope. So as Mario said, some preliminary machine learning knowledge is kind of required for the session. So I really hope that you're on the same page with us on all of that. So let me introduce myself. And while I do this, I would kindly ask you to briefly introduce yourselves in the chat. So if you can please say what you're doing in your life, so what you're studying, where you're from, what are some of your interests, just like maybe just a sentence on yourself. That would be great so that we can read some of them out. So let me introduce myself. I'm Jacopo. I'm an applied scientist at AWS, that is Amazon Web Services, based in Luxembourg, the country just in between like Germany, France, the Netherlands, all of those bigger countries. I'm from Rome, Italy, and I've studied at PoliMi, and I graduated just last year. So let me then pass it over to Virginia so she can introduce herself.
Yeah, hi, can you hear me? I think I had VPN that was blocking. Yeah, nice to meet you all. So first of all, thank you to the organizers of this event. It's super interesting and I'm happy to be hosting it. And hopefully it could be helpful for a few of you who don't know what machine learning is yet. Also, thank you to Jacopo who involved me in the first place. I'm working as well as applied scientist in Amazon, not AWS, and I'm based in Madrid. Working in the books team, so everything related to Amazon books. And I've done as well master's and bachelor's at Politecnico and focusing mostly on machine learning and deep learning. So yeah, that is me. I see many of you are introducing yourself, so cool. I think I'll leave it to Jacopo, who's gonna be leading the first part. Yeah, go ahead.
Awesome. Thank you. Thank you, Virginia. So yeah, we see we have like Felix. He's or she's from Ghana, studying geoinformatics engineering, interested in machine learning, and they're also from PoliMi. And then we have Hossein. They're studying electrical engineering from Iran, interested in machine learning. So I only see. Okay, no, we also have Melis from Turkey, studying mathematics engineering in PoliMi. We have Salvo from Milano studying computer science at PoliMi. So I see a lot of engineering, which wasn't really the case actually in our first seminar, where we would have also people from other, they were studying also something else. But that kind of makes sense if you think that this one is a bit more advanced. Okay, so we also have a lot of you who are also posting where they're from and all of that. So that's quite interesting. All right. Well, then I guess we can get started because we have a bunch of stuff to talk about today. So let me start sharing my screen. All right. So I'm guessing you can see my screen, which is great. All right. Welcome to Introduction to Machine Learning. Well, the first of a series of machine learning events that we are hosting, and this is the first session that we will be hosting. We'll also host a second part today, and Virginia will take the lead on that. So let's get started, I would say. So start with a refresher, or with one of the most interesting questions nowadays in ML, that is indeed, what is ML? So since theoretically many of you already know a bit of machine learning or have attended the beginner's track, why don't you type in the chat the definition of machine learning? So what comes to your mind when we say learning? We're going to try to make these sessions as interactive as possible. So we're really counting on your collaboration here. So does it have anything to do with artificial intelligence? All right, so I see a first answer, teaching a baby how to be a grown-up. Okay, I like that interpretation. And then we have Daniele, who's saying capacity or maybe capability of a program to learn from each iteration. Okay. And then we also have Omer, who's saying machine learning can be summarized by algorithms learning and changing from data, I guess. And I really like that I guess part, because we're not entirely sure as a scientific community, I would say, about one unique definition for machine learning, right? So there are some concepts that you guys mentioned that are for sure true and recognized by everyone, right? So machine learning systems, they take inputs, they take data to make predictions and decisions, unseen pieces of data, which is sort of like teaching a baby how to be a grown-up, right? Because you would teach them through some situations that happen, and that would be the data that is fed into them. And so that then they can learn and adapt to situations that they wouldn't have seen, right, when they happen. So I really thought Jaya Ram, sorry if I'm mispronouncing your name, said is totally relevant. And we can also say that machine learning is a specific field of AI where we have a system that learns to find patterns in some examples, that is the data that it sees, that it processes in order to make some predictions and to take some decisions. I think one of the first concepts that is taught in computer science, the definition of an algorithm, right, of a procedure. And the actual difference between, right, and you have an algorithm, a procedure, so deterministic procedure and machine learning is that you can always predict, you can always know what the, unless there is some randomization in it, outcome of an algorithm is. Instead, for machine learning, things are a bit different, right? And so why would we want something that is not deterministic? That's also something very interesting to think about, right? Why do we want to build systems whose behavior we cannot predict, we cannot know, and sometimes we cannot even understand why they would do something? And maybe the question is the answer itself to the question, right? Definition that we propose would be computers learning how to do a task without being explicitly programmed to do so, right? When we talk machine learning, when we teach also machine learning, we don't really teach them how to handle every use case, every situation, every variant of the environment that they as machines may found themselves in. And why can, right, this is a question for you, why can't we teach machines all of the possible combinations of the environment? Like, what is the actual problem? Why do we need machine learning, especially nowadays where we have the computational power? All right, so Gregorio is saying because there's too much data, right? And that's definitely the answer, right? There are too many situations. There are variants that are coming up every day, right? So sometimes you have a problem that is well-defined and already defined also in time, right? But sometimes you need a system that can adapt also to new data that you don't have at the moment. And so these are all very interesting and definitions that we can give to machine learning, and it's what actually makes the topic so interesting. So yeah, also in terms of computational complexity, representing all of the possible states or combinations of an environment is hard or impossible, right? So we need to address a subset of situations and teach our machines how to handle that, and then teach them and make them generalize on the other situations. All right. And so again, if you have any questions, please put them down in the chat. All right. So what are some things that machine learning systems do? They label or classify data, right? They can predict numerical values. They can cluster, so that means group pieces. It's very interesting, right? For instance, you can group behaviors of a set of customers, right? You can also infer association patterns in data, and you also can create complex outputs. So think about when we have a style transfer, right? If you have attended the first seminar, you might remember this, where we have an image and we take a paint and we put that painter's style on top of the image. I think that's super cool, right? So now let's try to think about some examples of machine learning used in nowadays actual situations, right? So first thing that comes to my mind, since unfortunately it's still relevant, there's COVID, right? Have you ever thought of some scenarios in which machine learning has helped with the current emergency of COVID? Or also, are there any other scenarios that you want to put down in the chat where we can find machine learning being applied to use cases, like real world use cases that are solving really hard and complex problems? And also the question is, could a human actually perform the same tasks in less time, or actually we need a machine to do that? So Gregory is mentioning scientific experiments with proteins, etc. They can be analyzed by machine learning, and that's definitely interesting. Google AlphaFold, it's a very interesting project that they're doing. Mind self-driving cars. So related to COVID, Alessandra is saying Google tried to predict where the flu would come by looking at Google searches. Okay, that's very interesting to know. If you can link an article to that, that would be amazing for all of the audience. Safa is saying better weather forecasting for increasing efficiency, renewable energy production. That's definitely super relevant. And the question is, could a human perform that task? Probably not. Weather forecasting is super hard. And in less time, I don't really think so. Okay, so we also have a lot of other examples. So thanks for putting them down. So again, let's remember that we can divide machine learning in mainly two parts. We can divide it in supervised machine learning and unsupervised machine learning. So in machine learning, we have that our model is trained on labeled data, right? So as you may see over here, we have our images, and these images are labeled with some words that represent the actual label. We call it label. We call it, yeah, I would say the outcome also of the of the task that needs to be performed, right? So if we imagine a task in which we want to train a self-driving car to understand the stop signs, or in general the road signs, right? We need to tell that car, unless we want to solve the problem with an unsupervised way, that those signs are stop signs. And so the car will learn to recognize them. On the other hand, learning, where we don't tell the car, hey, this symbol is a stop sign, this other image is instead a sign of like warning because there's traffic, or warning because there are people crossing. We don't tell our system that, and we let the system learn from the data unlabeled. Okay, so for instance, an unsupervised learning scenario is that of clustering, right? We give data to our model, and our model is able to cluster together, so to group together what is being fed to it. So for instance, in this example, it would group together these two, maybe because they're both triangle shaped, or because the center is white and black, right? So I'm sure you understood this, and maybe it's also a bit boring for you, especially if you've already followed the beginners seminar. But so let's look into loss. Let's get a bit, let's get our hands a bit dirtier. So has anyone ever heard of loss in machine learning? Or actually, maybe the question should be, have you never heard of loss in machine learning? Because I'm sure many of you have heard of loss in machine learning. So in the previous seminar, we also talked about linear regression, right? And I see some of you never heard about losses. Okay. So we have a problem in linear regression where we're trying to fit a line, right? The best line that passes, the best line that represents our data. And so we have all of this data, as you may see, these are data points, the blue ones, right? And we're trying to fit a line through them. So you may see 4 examples of 4 possible lines that we are fitting to this data. And so the question for you would be, which line do you think best represents the data between 1, 2, 3, and 4? Which line would you choose to represent this data? So please type your answer in the chat. All right, so I see a lot of you saying 3. Let's give it a few more seconds for everyone to type in their answer. So everyone is actually saying 3. And my question for you would be, why would you say 3? Like, why not 1? I like this line personally. Why not? Why, in your opinion, is this line not the best to represent the data? Also, what about line 4? It's not that bad. So Filippo's saying because the mean square error seems less. Okay, so we're already getting a bit technical with these metrics. The error of the sum of the squares in the third diagram is minimal. Okay, so similar question, similar answer. Because essentially the distance, right? The distance between the data and the line is less compared to the other lines, right? You can see like line number 1 is probably the worst, where here we have a huge distance, right? And instead, the sum of the distances here is lower than the others. And we can actually see here, it's maybe a bit small, but you here, where the loss is the sum of the distances, is very low here compared to the other. Okay, so there are not many questions on this, and so I guess now you know what a loss is. And a loss is measurable through many metrics. The distance is only one. We have the mean square error, mean absolute error, and the other metrics as well. So let's recap it very quickly on the concept of features. So what are features essentially? Features, we can define them as the variables which let us distinguish data one from another. So let's say we consider the classical problem of predicting the price of a house. And so houses are all different. Otherwise, life would be quite boring, I guess. And each one of us has their own house in its own location, with its own number of bedrooms, with its own size. And then for sure, there are many other things that really distinguish our houses one from another. For instance, the number of light switches, or the color of the walls in our house, or maybe also the brand of the table that your computer is sitting on. So there are a lot of features that describe our houses. And if we consider the task of predicting the price of them, perhaps we don't necessarily need all of them. And so it is very important in any machine learning problem to choose wisely the features that will give to our model. And why is that? Because one could say, well, if you only gave to your model the location of the house, then you could have a very big house and a very small house, and the model will predict them to have the same price. But one is way bigger than the other, and we all know that the bigger the house, the higher the price is. So maybe we also want to include the size of the house in our model. And then if we only have these two features, then perhaps we have a very big house, but that has maybe no furniture in it, and another one that actually is very well furnished with very valuable furniture. And so maybe that's also very important to know, right? But perhaps there are some features such as the number of light switches or the color, which is important to predict the price of a house. And so I really hope that I really made it simple, and there are no major questions on this, but it's very important not to fall into either having very little features or having a lot of features, which would then make every house very specific and not allow our model to generalize. This is another example where we consider the problem of recommending which video a user should watch next, right? So imagine Netflix, YouTube, Amazon Prime video, right? Where you can consider the topic, the popularity of a video, the number of views, also the creator of the video, perhaps also the actors that are in it, the genre. But is the length of the video important? Is the age of the video important? Maybe. And so you can see how all of these models, to build all of these models, is very hard, and many decisions need to be taken. And here I want to open like a very important parenthesis that's very relevant, especially when it comes to either research, both research and the industry. It is very important that as scientists, we do not make decisions on features based on our intuition. That could be the go-to if you're just starting training your model, and maybe you want to explore what your model can do with the data that you have. But when you present a report to a stakeholder, or when you produce a scientific paper, then you want to motivate the methodology with which all of your features, all of your data, why you excluded outliers, and especially how. So it's very important not to say, okay, I'll just exclude the length of the video. It's not important. I'll just exclude the main color that it's present in the video. It's not important. Like, come on. But you should find a way, given your features, to motivate why you excluded some or you included some other. And there are many methodologies to do that. So yeah, I hope that's clear. Anyway, so I would just let you maybe think a bit about, considering the scenario of the baker who would like to optimize pricing of cakes in their bakery, depending on previous pricing, cost to make, and time of the year. Like, do you think there's a benefit to the business? Do you think a human would perform the job better than a learning model? What could go wrong in the machine learning model? So feel free to take a screenshot of this if you wish, and think about it yourself. Because what we will be considering today is instead this other scenario. So let's talk about this a bit together. So we have an ocean conservationist, right? So a person who's very interested in the, we can call it health, I guess, of the ocean. And they would like to track fish population over time. So, like, what do you think? Is there actually a benefit for us as a society? Because, okay, it's important to know how to code. It's important how to know how to build a model. But these questions are very important because as scientists, we should always have a purpose on why we're doing things and why our problem is relevant to whoever is the customer of our analysis. And so, like, what do you think is the benefit for us as a society? What do you think about the scenario? Like, what should we have to make this problem actually solvable through machine learning? For instance, should we have, what kind of data should we have? All right, let's see some answers. Oops. So yeah, we definitely want to preserve the ecosystem. Yeah, so that's definitely important for us as a society. If the fish is hunted by us, then tracking the population over time can help with regulations about the hunting season, of course. Gregorio is suggesting videos of fish as data. Okay, how would you use videos of fish to track the fish population over time? You mean like videos of, like underwater videos of fish? Yeah, okay. Yeah, so we could have, in Gregorio's opinion, maybe if submarines, I don't know, they didn't run on maybe fuel that pollutes, we would have like some, or you mean like underwater cameras? Yes, that could also be happening, but to look at the fish population. But maybe the ocean is a bit too big for that. So Surerbus01 is suggesting to track how much food they ate. Okay, how would you do that? Ulmer is suggesting the species-specific data can be useful. like mating season, how many offspring on average get to mature into adults. Yeah, that's definitely interesting, relevant, and important. Historical data, of course, about fish population in other places. Salvatore is suggesting GPS data. So yeah, it depends on the fish. Some bigger fish are definitely tracked through GPS, and that's very relevant. So anyway, we need a lot of data, right, to understand how fish population evolves over time. And of course, it's important for us as a society to do so. And why? Essentially because we are able to identify if a species is endangered. So if there is some species that that its number is reducing in time very quickly, or on the other hand, you could have a species that is developing too fast. And so that could also be a problem for our environment. And so what kind of inputs could we give to the system? So that could be the type of fish, right? If we want to track a specific fish population or many fish population, then the time of the year, the number of fish. And so the problem here could be that the ocean is too big, right? And so we definitely need a sample to solve this problem, right? Because for instance, SurBus01 is suggesting us, I register the food I introduce in the lake and control if they ate all of it or it is in excess. So you can do that when you have like a lake that you can actually monitor, right? So you can monitor what goes in. Maybe monitoring what inside the fish belly is a bit harder. And monitoring also what's left over is a bit harder, but it's definitely a very hard problem if you take as the data, if you want to measure data that is very hard to measure. And so we could see this problem as a very hard problem, also because it's in the water, it's not like in open air. As humans, more difficulty to solve this problem. And so there are a lot of answers actually to question number 5, where you have, how could the machine learning model go wrong? And the main answer to this would be data. And this is definitely a very recurrent answer when looking at machine learning models. If the data is not diverse enough, if the data is not enough, if the data is not representative enough of our environment, then we might end up being able to make good predictions on the specific environment that we're looking at. So that could be, for instance, the lake that SurBus01 was referring to. But then we're not able to generalize over all of the fish population that we're tracking. So it's very, very hard to solve some problems. And so we cannot conclude that machine learning can solve any problem. It really depends on the data that we have. There is also another scenario that we can think of, but I'll let you take some time on your own to then think about this. So this would be an online brand influencer wants a model that can predict the number of likes that a particular post will get. And so this is definitely more also like a problem that's maybe closer to us as we use social media. And so you might want to get some examples from social media itself. But again, as analyzing social networks is not an easy problem. And so, yeah, I'll just let you think about this on your own. And please also your own scenario in which you think about a problem and you say, oh, maybe it's not really applicable to a machine learning, like a machine learning model is not really applicable to this scenario. So besides these last examples, I really hope that this first part recap on machine learning was quite clear. So just to recap what we've seen what machine learning is, what are the typical scenarios of machine learning, such as labeling data and making predictions. We've also discussed about some real world machine learning applications. We talked about the difference between machine learning supervised and unsupervised. I will also remember you that there's also reinforcement learning as a third field of machine learning. And then we also talked about loss and features. Loss being what we as scientists want to minimize in our model, and features being the variables that describe our data. And finally, we looked at some examples on that may be solvable through machine learning, but are not trivial, and many variables are to be taken into account. So if you have any questions on all of this, please type them in the chat. I will now let Virginia take over so that we can continue with the second part of this workshop.
Yeah, okay. Thanks, Jacopo. That was a great presentation and hope it was clear for everyone. So I'll share my screen. Just a moment. Can you see it? No, sorry, I have to fix the system preferences. Okay, can you see my screen?
Yes.
Okay. Let's see, just a moment if it's loading. Sorry, it's the first time I'm using this, so it's that. Does it say it's still loading? Well, can you see it now? Maybe.
No, we see it still loading, or at least that's what I see.
Okay.
It's
We'll
fine.
give it-
Maybe we can take like 2 minutes to maybe go to the bathroom or have a glass of water, and in the meantime we'll solve this. So if you want to take like a second, if you want to go to the bathroom, that's what you should do right now. At worst case, Virginia, I can share my screen, and I mean, feel free to try again, but let me also open it here. So.
Okay, I think it's visible
Okay,
now.
now, yes, now it's visible. So let's wait maybe 1 minute and then we can start.
Okay, I think we can start now. Okay, let me know if you have any issues still seeing my slides. Okay, so we're gonna move to the second part of this first session. In the first part, so we had an overview of what is machine learning, what are the different types of problems, and in the following sessions, we're actually going to be solving some of these problems by actually coding some solutions. But before putting our hands on and really actually solving through code, we actually have to understand how we should approach a problem when we first find it. So let's say we have an intuition of a problem that we think might be solved by machine learning. How do we actually really start solving the problem? So we can't just jump into the code. We have to define basically a framework in which we're trying to solve this problem. What we're going to do is basically start from our end goal. So we said that machine learning systems are actually used to make predictions that allow us to make some decisions in the real world. So this is actually our goal. So we're not going to build a model which is going to be able to make a prediction with 100% accuracy, and then it's not even useful to do our end goal to complete our task in the real world, because that's what we really want to do. So we're starting from a decision we want to make and understand how we can work backwards to build a machine learning system to be able to make that decision. So this is what we call problem framing. So what we saw in the previous lesson is what is machine learning. And also we did try to do a first distinction between the different types of tasks we can find in machine learning. And what we're going to be doing right now is focus mainly on supervised machine learning. So I'd like to give you now a bit of time, like 90 seconds, if you can think again, if you can remember what was the definition of supervised machine learning. Try in your own words to get an explanation and maybe write it down in the chat, and then we can discuss it. So I'll give you like 90 seconds or a minute. I see no one writing yet. Do you remember what it is? Does someone remember what supervised machine learning is? Okay, so we have a first answer. Label the training data with the desired output. Okay, yes. Any other one? Anyone else wants to try? Training with labeled data. Okay. When a supervisor judges the result of the ML algorithm in terms of usefulness and correctness. Okay, well, this is another definition. I think we can go with the definition of actually training having labeled data. So this is training a model based on already seen data. Well, actually, we always do train a model with data that we have seen, which is historical data that we have in our data sets, to be able to make predictions on something we haven't seen before. But yeah, we're getting to the concept. In supervised learning methods, it is necessary to have samples of all data so that I can teach the model well. Okay, so I think more or less you all got the main idea of supervised machine learning. So as Jacopo mentioned as example, basically with machine learning, it's like teaching a kid to start doing a task. How is he going to learn to do a task? So probably he's going to be learning by examples, by some associations. And learning from those, he's going to replicate that task. Maybe it's some specific behavior. So supervised machine learning consists of machine learning systems where we feed them with input that has a label. So let's think of examples. We have examples in our daily life. For example, we receive an email which could be spam or not spam. What we can do is actually build a machine learning system which distinguishes between an email which is spam or not spam. What we can do is teach a model to learn the distinction, having looked at some examples. So an example would be an email with a label which is spam or not spam. So this is what we mean when we're talking about supervised machine learning. So the opposite would be unsupervised. We do not have labels for our data. The goal of using a machine learning model is to try to identify some patterns that are within the data, which out, and we're not going to tell the machine how to find these patterns. This is the cool thing of machine learning. We're not going to hard code what the system needs to be finding within the data, but it's going to be finding that on its own. So we're going to be focusing mostly, as I said, on supervised machine learning, which is, let's say, easier because we have examples from which we're learning from. Although we should take into account that nowadays, with the huge amount of data that we have, which comes from the internet, it can come from social media or news, or every day there is a whole lot of new data that is being stored. And what do we do with all this data? We need some models which are able to deal with this data, which is all mostly unlabeled, because mainly to label a data, we need a human. It's most of the time is going to be a human to manually assign a label. But we're going to be focusing on supervised machine learning for these sessions. So moving on, we're talking about label data. Let's give a bit of terminology so so everyone understands clearly what we're talking about. So as many of you mentioned in the chat, so label, we define as label what we want to predict. So in the case that I was telling you before, predicting whether an email is spam or not spam, the label will actually be spam or not spam. So in this case, it's a category, it's a class, and we have two of them. We're trying to predict between one or the other. A label not only has to be a class, it could be an exact number. For example, when we're talking about regression problems, what we want to do is predict a precise value. For example, we want to predict the stock value, the value of a stock tomorrow, or we want to predict what the weather is going to be like tomorrow, for example, the maximum temperature. Even that is our label. But what is a label associated with? So a label is associated with a set of data. So in our data set, we have input variables, which are matched to a label. The input variables are what we feed our machine learning model with. And the machine learning model must learn from these inputs to be able to predict the output, to predict the correct label. So we can define these set of inputs as features. This is typically the name that we give them to. So features or input variables, the same thing. We can enumerate, we have features x1, x2, xn. For example, in the previous slides that you saw before with Jacopo, you had a problem with the linear regression. So when you're predicting a line, one of the variables is x. So the x-axis, or we can have x1, x2, xn. So we define an example as a particular instance of the data, and we call it x. So x will be a vector which is a set of features, essentially. In the example that we saw of the email, which could be spam or not spam, let's see if you can think of what could be the features that we give our model to as input, and then we label them as spam or not spam. Why don't you try and write in the chat what you think in this case could be the features of our model? I see there is a question also by Gregorio. Can we do machine learning with labeling so I don't have to label? Actually, there are some models right now which are used to perform automatic labeling. They start from a small set of labels and they do labeling, but this is another topic, so we can maybe discuss it offline. But let's see, try to give examples of features in the scenario of spam or not spam. What do you think could be? So I read presence of many grammatical errors. Okay. Let's say the title of the mail is with full capital letters or not. Yes. The address of links, the words used in the mail. Okay. The sender address, sender domain. Yeah, these are all good examples. In this case, it might be quite obvious for us as users to identify what could be some good features. For example, you see the word free or competition, you want money, or you look at, as you said, the sender address, many links. All of these are good features. Then you have to find a way to well encode them to be able to feed them to the machine learning model. But then from these set of features, which you think might be useful, you can predict an output. But let's not make the mistake that Jacopo has already made us aware of, which is just feeding features based on our intuition. So we're gonna just say the number of links in the email and get a prediction. So maybe this model might work. Maybe it is sufficient to check how many links there are in an email to get a good prediction of spam or not spam. But the cool thing of machine learning models is that you don't need to know exactly what is the right feature you should be feeding the model with. Many times it's going to be learning it. So one example in this email spam detection could be we're feeding as input all the text of the email. And this is actually what many modern machine learning systems do, which process text. Many times, these are actually now working a lot better than building your own features. This is then something maybe you're going to see later on. But one example of a feature X could be just feeding the whole text of the email. And let's move on with the terminology. So we said we define our set of features. We assign them to a label, which a human annotator has given. And now we have a labeled example. And we can use this to train our model. So our model will be able to learn patterns from the input data to be able to make a good prediction. Well, this hopefully, it's not going to be all the time like this. On the contrary, if we do not have a label, we're going to call this unlabeled example. So these examples, we can use them to make, for example, predictions. So this is our new data on which we want to test our model. Or as we said, unlabeled examples are used. We can use unsupervised machine learning system for these. And then we've repeated this word many times. What is a model? So a model will essentially be an algorithm which is able to match the inputs that we have, which is the features, to the predictions, so to the labels. So it's going to be finding the relationship between input and output. And it's this relationship which we are interested in finding. And how do we do this? So what the model is actually learning is some internal parameters. If you think of the example that you saw in the previous slides with Jacopo, the example of learning a line from data, well, the basic equation of a line is y equals alpha x plus beta. What we're going to be learning is actually the value of alpha and beta. So that is what is defining our model. Our model is defined by its internal parameters. Okay, so here I have an example of machine learning in the news. So from this part on of the presentation, we're going to be looking at really concrete examples of where we can apply machine learning and whether we can apply machine learning. So we want to try to build a framework to see whether, how can we do, starting from a problem which we think machine learning is able to solve, can we frame this problem? So which are the features we need to solve this problem? Which are the labels we need to associate them with? Do we already have any algorithm which is good enough to solve this problem? Or can we do better? Can we use machine learning to do a bit better? And then when we build our model, how do we analyze our results? How do we compare them? Was our intuition correct? So we're going to be trying to do this. So I'm going to be sharing a link in the chat. And this is a real example of an application of machine learning. This is basically a group of researchers used a machine learning model to predict whether people had skin cancer. So I'll give you a couple of minutes to have a quick read of the article, maybe just scan it through, try to understand which are the key concepts. And then we're going to try to look together at what the article was saying, basically trying to frame the problem. So the problem is that of predicting whether a person has skin cancer or not. So you'll try to have a read at the article, trying to understand what these researchers used as features, which were the labels, and how we might analyze the output. So I'll give you a few minutes, and then if you have any question, just write it in the chat, or if you already have some ideas of framing the problem, just go ahead and write, and I'll start reading them. I'll give you a couple more minutes to just go ahead and screen the article. You don't have to go into every detail. Also, this is written for wider public, so there's not that many details we're interested in. We're looking at trying to frame the machine learning problem. Okay, I see Samuel is saying already the labels are malignant carcinomas and malignant melanoma. Okay, correct. Anyone else want to try to guess some of the features? Or even go ahead and say something you think might be a good feature. For sure, in the real world, as scientists, we should be able to understand which are the correct features that we want to use in our model. But we're not dermatologists here, so let's try and give it a guess. Okay, Gregorio says the image. Yeah, exactly. Let's see if someone else gives it a go. And then we're going to discuss whether it is the image or other features. Okay, we have the features are the color of the cancer cells, their area. Okay, yeah, these are all good guesses. So, well, let's start from the label, maybe. Let's start discussing it together. If you have other ideas, I'll be reading and we can discuss it. So the label, as you saw, we have a malignant carcinoma, malignant melanoma. Let's make it a bit more simple. Let's label it as has cancer or doesn't have cancer, because we also want to include the case in which there is no cancer. So let's reduce it for simplicity as this. So the labels are diseases in English. The features can be the shape, coloration. Okay, yeah, as we said, the labels, let's do it for simplicity as having cancer or not, but then we can go into a bigger level of detail and specifying all the types of cancers, of skin cancer. When we're thinking about the features, it really depends also on the model that we want to be using. So one thing we can do is try to find a set of features which could be useful to solve the task. For example, in the case of skin cancer, we're going to be looking at moles. As what dermatologists do is they analyze the skin, they try to find moles and analyze, as you guys said, the area, the color, the shape of it. All of these can be features which we give as input. Although there is one risk of using this approach, if we're not experts and we know the exact features are going to be useful in making the prediction. One other solution which we can use is using, as Gregorio said, the whole image. So basically, when we're feeding the whole image, we're incorporating many different information within this. So from the image, one can understand the area, which is the shape, which is the color. So we're already giving all of this information, not having to encode every single information in a different way, so like encoding the area, encoding the color. So one good solution is actually feeding the machine learning model with the image. So it will be the model itself that will understand whether it is important to look at the color, the shape, the size. So this is one good thing of machine learning. This doesn't mean that engineering features is not useful. Also, if we, it depends on the model we're using. And also, if we feed an image, we're going to get a more complex model and a bigger model with many more parameters. Does anyone know how we can encode an image to give to a machine learning model? How can we encode it to give it to a whichever algorithm, an image? Can anyone guess? Yeah, it's a matrix, exactly. If we have a colored image, it's gonna be a three-dimensional matrix where every value is the value of a pixel. So if it's a colored image in RGB scale, this is why we have three dimensions. So actually an image is quite heavy. So we're going to get a pretty complex model, which is going to be learning from a lot of data. So the advantage of using even a reduced set of features and engineering correct features is actually to have a more simple model. If we think of the previous example that we were making about spam detection, one solution that you said is, for example, looking at if the subject of the email is in capital letters, if we have many links. These are all very small information that we can encode and give to the machine learning model. If we're feeding it with the whole text of the email, we're going to feed it with a lot more data. So it's going to have to learn a lot more parameters. So we're going to get a more complex model. So this is always going to be a trade-off. So how simple you want the model to be, how complex you want it to be. But for sure, one of the most popular approach nowadays in industry is using the whole image and using a model, for example, a deep learning model, to extract relevant information to be able to make a prediction. So we've covered most of the terminology here. What is the output going to be? Well, the output is going to be our prediction. So whether an image is associated to skin cancer or not. Okay, so once we've looked at this example, I think we're able to identify a framework and a correct methodology to follow when we're looking at a problem and we think machine learning could be useful to solve it. So first of all, we have to frame the problem. As we said before, we want to understand if a person has skin cancer or not. This is our problem. Another problem that we have in this slide, for example, we want to understand what will the traffic be tomorrow. So once we have framed this, actually before step 2, which is make a hypothesis, I would first ask another question. Do we already have a model which is able to perform this task? Because if we do, we should first understand, is this model good enough? Do we need to build a better solution? Because many times we're fascinated by machine learning. We think it's the solution to everything, but maybe there already is a better solution and we don't really need to start solving this problem at all. But then once we have framed the problem, let's say we don't have another solution for it, let's make a hypothesis. Because what data are we going to be using to solve this problem? So we need kind of an intuition here. One hypothesis we can make is that we think that the weather is going to influence traffic. So we think that weather forecasts can be informative. So how do we know if it's informative or not? Well, we need to first of all gather the data. Do we have this data? How can we gather it? So let's assume we have a data set of historical data of traffic that we have in a specific city, for example, every day of the year, and which was the weather in that specific day. So once we have collected this data, we want to test our hypothesis. So is there really a correlation between one and the other? So what we're going to be trying to do is train a machine learning model that from from weather data, is going to be trying to make predictions about traffic. And is the model good? Is it good enough? Is it better than any existing system that we have? So at this point, we're going to try to analyze the results and see whether we made a good hypothesis, which it could be true. We could reach the conclusion that the model is useful. We should use this model to solve this problem. Or maybe it's not useful. Maybe we're not getting accurate predictions. Maybe the existing system is already good. And what happens if this model is not good enough? Should we end it here? Well, maybe we can go back and change our hypothesis, try to understand what went wrong. Maybe we need some other data. Maybe the hypothesis was correct, but we need more data. So then we have this step of refine and repeat. For sure, not forever, because at some point we might understand that probably we cannot solve this problem with this type of data. we should move on to a different approach. Okay. So what we've seen so far is actually trying to frame a problem. So what I'm going to show you now is a few slides where I'd like you to do this on your own, and I'll leave it to you as an exercise, since we've already done a few together, of trying to really frame a problem like we've done in the case of the traffic. So for example, I'll read you this problem. So you have a landscaping business that wants to hire people for the fall season. So what you want to do is trying to understand how many people you want to hire. So how many people do you want to hire? What is it going to be based on? So you want to predict how many leaves will fall from each tree. And based on the number of leaves, you're going to be able to predict how many people to hire. So what we've seen is how we're going to be framing this. So I'll start giving an intuition about it, but then I'd like to leave you guys these as an exercise to try to get into the practice of framing machine learning problems, because that is what you're going to be doing before actually moving just to the code. You have a problem you want to solve. You have to frame it at the beginning. Understand if you have a clear use case. So do we have a decision that we want to be making based on this problem, based on the predictions that your model is going to give you? Do we already have a model for this that we can compare it with? Do we have the right data to be able to solve the problem? Do we have enough data as well? And the predictive power means from these predictions, can we actually make the decision that we want to make? So in this case, we have predicted correctly the number of leaves. Can we now make our final decision, which is our business decision, how many people to hire? So what this last point is saying is exactly, we're aiming to make decision, not just predictions. We don't want to make machine learning models just because it's fun. We want to get a prediction and it all ends there. We want to build them to make a decision, so in order to be useful. So I'm going to leave you a couple of problems here that if you want, you can have a look. So this problem is a beekeeper wants to analyze pictures of their honeybees and identify their role within their colony. Then here a second example, a teacher wants to predict a student's end-of-year test result based on a student's performance on mini tests throughout the year. So here, do we have the right data? Is this problem actually solvable through machine learning? You should ask this question a lot, because not everything can be solved with machine learning. And then maybe a more interesting example, choose an organization who would benefit from a machine learning model, explain what the proposed model will do and how it will impact the business. So this can be very interesting, even maybe for preparing for interviews. I think this is a really cool example. Okay, so I think this wraps up this second part of the lesson. So I think we can already move on. If you agree, Jacopo, we can move on to the question and answering part of the class.
Yes. Let's spend these last 10 minutes if anyone wants to ask any questions or literally anything to us about what we just talked about, or also anything else. Also, let me remind you, as I always do, that there is a fantastic platform that is LinkedIn, right, where and I really invite you to connect with us and please just write us any other questions you may have. Personally, I'll be super happy to answer them, and I'm sure also Virginia shares her availability on this. So
yeah, both have. If you have any question now, go ahead and speak up. Otherwise, we can even bring it offline if you have anything more you want to get into more details, or maybe unrelated to with the talk.
Yeah, and also get ready, because we are getting ready for Tuesday's session where we'll actually have a demo and a workshop. We're going to see some TensorFlow. So that's going to be quite interesting. So Vlad asks us, could you spend some words about what an applied scientist do? So yeah, for sure, it's interesting to see the difference between a software engineer, a data scientist, a machine engineer, a research scientist. I don't know, Virginia, maybe you want to share something about it?
Yeah, I mean, the definition of applied scientist, I would say that depends on the company. So we can probably give you a definition of what we see within Amazon, which is more or less similar to other big tech companies. But there are other companies where the data scientist is the role which gathers basically all of these other roles. It's going to be doing machine learning engineering, an applied scientist as well. So the definition of applied scientist, basically you are both a data scientist and an engineer. So what you're required to do is going the whole process from research idea, go through the whole process of investigation, data analysis. But when I'm talking about engineering, it's because you actually have to be able to build a prototype which should be can be deployed into production. Then actually you're not going to be working on the deployment because it's not your role, but you kind of are a figure that should be able to do all of these things. Sure, my day-to-day would be using machine learning, I guess. Without machine learning, you can't do applied science in these days, but not all the time. Not every day I'm using machine learning models. But let's say it's kind of a requirement to know a lot about machine learning because it's now in the industry, it's used across a huge variety of tasks. So this is one thing you're required to use. What else can you say, Jacopo? Well, distinction. Distinction, let's say, between the other roles, maybe data scientist is, for instance, in Amazon, is not required to be able even to build a prototype, which is fully working for deployment, for production. Machine learning engineer is going to be working on maybe, a variety of things, but working mostly on the deployment of your model, building maybe even data pipelines. Well, maybe that's more of a data engineer because there are many classifications. But the ML engineer, maybe it's gonna scale your algorithm for, if you have a large scale, or help you in the training process, training on multiple machines.
I think the problem is that there are so many problems in the industry and in research. And for sure, what you said is totally relevant. So you can really see an applied scientist as the combination of a software engineer and a data scientist.
Yeah, a fully rounded figure, let's say. We're required to do it all.
Yeah. So let's see. Maybe Virginia, when I talk, if you want to put your mute, because I can hear my voice in the background. I think, yeah, fantastic. Thank you. So we have Jayaram, sorry. In your, what should be the mindset, thought process of a machine learning engineer, or what is the mindset a machine learning engineer have? Wow. Okay. That's a very long question, I would say, to answer. And so let's say if we're not able to answer that through what we've presented today and what we will present on Tuesday and next Thursday, then we can go back to it. Okay. So we can also understand through the workshops what is the thought process that we will employ as ML engineers. So yeah, essentially, the workshops will be mostly on supervised learning. Transfer learning, can you say that supervised learning, Virginia? I don't know. Is it?
It is.
Yeah.
Transfer learning is basically using a model which has already learned on another, a different set of data than the one you're using. Usually it's going to be a bigger set of data. So you already have a machine learning model which has some prior knowledge instead of learning from zero knowledge, but it's still learning. It has, in this prior task, it learned with labels, so it was supervised. And when you're performing transfer learning, it's basically you're feeding this already trained model with new data, which is always labeled. So it's still another supervised task because you want it to learn not from zero, but from a prior, and learn on new data. Yeah, and
I
also
have a question for you, Virginia. Just out of curiosity, have you ever heard of instead unsupervised transfer learning? Because I've never heard of it. So when you have like a model that is unsupervised, and then you use that model you trained on unsupervised way, because I've never heard of it, but I'm sure somebody experimented with it, but we should investigate on that.
Never heard of it. There's other things, as you said, I mean, reinforcement learning, but also now a lot is spoken about self-supervised learning, which is in the field of natural language processing. So an example is these models which are able to generate text. So maybe you've heard of these names, GPT, BERT, all of these models. What they're able to do is predict text from a sequence. So you're giving it, for example, a sentence, and you want it to complete the paragraph after this sentence. So this is called a self-supervised because you don't really have labels. You're learning from your data and you're, let's say, creating a label of your own. Now, this would take me a lot more time to explain, but just to get an idea that there are many different tasks right now in machine learning. Also, I don't know, GANs are combining supervised and unsupervised. If no one has heard of GANs, it's generative, what is it? With generative
networks.
Yeah. Basically, networks that are able to produce new images. For example, I love this example. I'm gonna send you a link. This is a website where you can, every time you open it and you refresh it, you get a new picture of a person which actually does not exist. So it's basically a GAN network that has generated it. The one that generates fake people, exactly. You can do a lot of things, generate fake news, anything you want.
Crazy. That's super crazy. Yeah, these people really look like they actually exist.
Yeah, it's impressive. Nowadays, that's why there's a lot of research being done on detecting fakes.
So all of this is super interesting. In the meantime, I was also having a look at unsupervised transfer learning. I see some anomaly detection here. So for sure, it's definitely interesting to investigate this. So if any one of you is interested in unsupervised transfer learning for some reason and they want to, I don't know, spend some time and find some resources that they want to share with the group, feel free to do that either during next session or also in the Telegram group that we have as a Google Developer Students Club. And what else? I would say maybe we can answer. Oh, where can we get?
Question about also our opinion about Politecnico. Well, this opinion probably is going to be biased because we're both from Politecnico. To be honest, I have just a very positive opinion of Politecnico. So both of us, me and Jacopo, were focusing mostly our masters in machine learning and AI. And I think, I mean, in my experience, I had very great courses, especially with Matteo Matteucci on artificial neural networks. You're going to get hands-on and use TensorFlow, for example, but even other courses, recommendation systems. So they always say that Italian universities don't do practical things enough, but I think in our masters, there was a lot of projects that helped us then gain knowledge to then start working. And also an advice is focus, get a good thesis advisor when you're going to be working on the thesis, get a great topic you're interested in, and spend time on it, because that's going to help you a lot even on your job. For example, for me to get into applied science, if I hadn't done my research thesis on deep learning, if I hadn't done that, I would have never gotten the job, like never. They would have asked for a PhD.
Yeah, most definitely. It's very interesting to already start practicing some research, already doing your master's. I wouldn't say your bachelor's at PoliMi, but there are many opportunities. I would say it's on you to take them. So PoliMi won't come to you and say, hey, we have some research, let's develop it together. It's more on you to find your interests, your passions, and to find a very good thesis advisor and explore what you really like. So maybe that would be a difference between PoliMi and other universities, especially outside of Italy, where maybe you're more guided towards some goals and achievements that are required also by jobs many times. And so definitely follow these advices, I would say. But yeah, and we also have which kind of master did you do? So Virginia and I did the same. We were doing computer science and engineering at Politecnico with a focus on learning and AI. So all the professors such as Matteo Matteucci or Professor Gatti, Professor Amigoni, they're the ones teaching these courses on AI, machine learning, and there are many more professors. So yeah, I would say that we can close it off here for the session. Really looking forward to Tuesday, where we're going to have a first demo where we're going to see actually an example of machine learning through TensorFlow. That is a machine learning library developed by Google. And then we'll also have a workshop where you guys will actually be challenged to complete some machine learning code and train a model.
Good. So thank you very much for joining us today. Thank you to Jacopo and Virginia, of course, for presenting and being patient with us and explaining all of these things. And we hope to see you on Tuesday. So have a nice evening, and thank you so much for coming.
Right. Thank you all.
Bye.
Bye.